Welcome to the second class meeting of EECE574, the graduate level probability and random processes. Here are some announcements. The PDF file for the first class meeting and handout for this class meeting 2 are uploaded at our lab homepage, not PLMS, okay? Most of the course materials will be available from the lab homepage. So you go to my lab homepage, find teaching, find the this course, and you will see all the materials. Of course, sometimes I will send you announcements through PLMS. I will also put some announcements on PLMS, but you can still access that in the course web page. So course web page would be the primary web page for this course. Unfortunately, due to the technical difficulty, we have no recorded video for the class meeting 1. From today, we are going to record everything. So if you are Korean students and you are not feel good at my poor English, then you can just view the recorded one. By the way, I appreciate our staffs of the department who could replace our computer to resolve that problem, okay? Homework 1 will be posted on the PLMS, and whenever I post the homework, then I will send you an email or I will send you a short message to your cell phones. So in that case, you go to the PLMS and find the homework and sometimes upload your homework there, okay? And the homeworks may not be available from the primary homepage. Corrections, clarifications, common mistakes, Q&A. This time there is none. Here goes the overview of this entire course. As I told you, I'm assuming that you have taken the undergraduate level probability random variables and random vectors. So even though you didn't take such a course, probably you would have taken probability and statistics course, and that would be enough, I hope. So I'm going to supplement those undergraduate courses by providing you the knowledge on random processes as we have started last time. And also, I'm assuming you have taken undergraduate level digital communications course because most of the applications and homeworks related to random processes will be more communication oriented or signal processing oriented, okay? By the way, I mentioned the extra credit or voluntary project so that you can avoid getting B- in this course. So whenever you feel, okay, something's going wrong, then be prepared for the voluntary or extra credit homework, extra credit project. If your result is satisfactory, I will upgrade your final grade one click. So, and the format is PowerPoint with recorded voice, okay? So you have to present something not in front of me, but for example, in your dorm, and you record 15 to 20-minute presentation with a PowerPoint slide or PDF, anything. Then you submit through the Postec webmail as a large size file, something like that, so that I can download it with no problem. Got it? Okay. Last time I asked you what is a definition of a random process. Precisely speaking, that definition was not a major theoretic definition. So it was a non-major theoretic. Just a second. I don't like this color. Okay. So non-major theoretic definition we've seen. And today we are going to see major theoretic definitions because it motivates us the concept of sample path. Many of you have already heard of the concept of sample path, but many of you, I believe, were kind of perplexed at the notion of that. So I'm going to talk about major theoretic definition and contrast it with non-major theoretic definition. And the key to link these two definitions is what? We've seen some guy's name last time. What? Yeah, Kolmogorov's existence or extension theorem. Got it? So that is very important. And we've seen non-major theoretic definition, and that definition required some notions like first order CDF or PDF of a random process, second order, third order, nth order CDF or PDF of a random process. That those definitions were related to non-major theoretic definition of a random process. So probably many of you would never use major theoretic definitions of a definition of even a random variable. Probably you would use CDF, PDF, probability mass function, those things only. No sigma algebra, no Borel sigma field, something like that. However, we need those concepts in some applications, especially when you talk about sequences of random variables. In order to talk about the convergence concepts, convergence modes of a sequence of random variables, we definitely need major theoretic notion. So we cannot avoid. But to many of you, it will be just one topic in a graduate course and you will never use. But anyway, it's good to have that knowledge. Got it? So preview. We are going to talk about major theoretic definition of random something. It would be random variable, it would be a random vector, it would be a random sequence, it would be a random field, random graph, random anything, including a random process, okay? And there, Kolmogorov's existence or extension theorem plays an important role to link this non-major theoretic definition of a random process and major theoretic definition of a random process. And as I just told you again and again, the notion of sample path or sample function just appears naturally from this major theoretic definition. And we will talk about underlying probability space too. Okay, got it? So this is today's picture. And as I posted in our course webpage, I'm going to use this undergraduate material from the Peebles textbook. If you go to the PLMS or our course webpage, I've listed this Peebles textbook as a reference book, okay? And after we cover many topics here, we are also going to use some of the populist material, okay? So you may just think in this way. This course covers the last half of the Peebles undergraduate textbook for probability, random variables, and random process. Okay? And also it covers the middle chapters of the populist textbook. Got it? So let's see. The random process concept. Before I talk about random process concept, let's remind us of a major theoretic definition of a random variable. So anybody, what is a random variable? In a major theoretic sense, what is a random variable? Anybody? Right? So random variable, mostly you have a concept like this. Okay, here is a variable. If it has some uncertainty, it is a random variable. And random variable is described by a PDF, probability density function, or probability mass function. That is not a major theoretic definition of a random variable. It's a kind of white lie for undergraduate students, okay? Because most of our human beings do not need major theoretic definition of a random variable. However, as our classmate just mentioned, major theoretic random definition of a random variable is this. It's a measurable function. So it's a function. Random variable is a function. What does that mean? Function has what? An input and an output, right? Function is a mapping rule. Of course, you have no idea what is measurable, but as I mentioned, this is a measure theoretic definition. Probably that measurable function, that measurable, the term is somehow related to the measure theory. But anyway, it's a function. So there is a box with input and output. Now, since a random variable is a function, what is the input to this random variable? What is the input? And also, the question is, what is the output of this random variable? What is the input and what is the output? Okay. So since it's so abstract, let's think about a concrete example. Suppose you are tossing a coin. Let's map heads to 0 and tails to 1. Okay. Then what happens when you toss a coin? What happens? You either observe 0 or 1, right? And you have some urge to say that, okay, output is that value, 0 or 1, okay? So far it's okay. So in coin tossing case, this output would be an element of this set, 0 or 1. Now, what is the input? And you may say that, is there any input, right? Because to us, communications and signal processing engineers, random source does not have input. It just generates some output, right? That is called a source. And in undergraduate course, you may have drawn this kind of box. Okay. Here is a source. We have a random variable x. We don't know what does that mean, but we said we have a random variable x that takes either 0 or 1 with a probability of 0 equal to 1/2 and the probability of 1 equal to 1/2, right? So it seems that something's missing there if we say that a random variable is a measurable function. Because in our undergraduate program, there was no input. This is kind of undergraduate visualization of a random variable. But now we say this, right? So this is very, how to say it, confusing. But anyway, we need something here. And what we are going to do is that we need to put these together and say that actually this entire box corresponds to this one. Okay, got it? Now, what is that box then? And here goes the notion of a probability space, okay? And random experiment and abstract probability space. And this box generates some output. We say lowercase s, okay? We don't know yet what it is. And as our classmate said that the right side box is a mapping rule, so it must be let's take that s as the input. And usually for that kind of mapping, we have had some notation, something like this. For example, you have a function f of x equals x squared plus x. But this is a kind of shorthand notation. What we have to do is that the function is what? A mapping from, for example, r into r. And the relation between input and output is this, right? So you have to define this way. You have to specify domain and range, right? Similarly, we want to define the domain and range of this box. And also we want to name this one. And we name it X because we named the output of our undergraduate version as X. Okay, so we are going to use the same thing. So here goes X. So now we have a function of something. And this something we don't know yet. And here, this box is a new source that drives this random variable. Got it? And kind of, it's like we kind of divide this into two boxes. One is a simple function, and the other is a random source. And now this random source is described by a triplet. A triplet means that you have one kind of thing consisting of three subcomponents. First one is what? The sample space. Second one is called the event space. And the third one is called probability measure. This box is described by these three things. But what is this box? This box is, you may assume that, is a random something generator. Got it? And that random something generator generates S in this sample space, so-called sample space. Got it? So the output of this box is a member of this first entry of the triplet. Now, I said this is a random source. So what you want to do is that we talk about the probability of event that this outcome S is a member of something. For example, we want to say that, okay, what is the probability of your observing 0 or 1 when you toss a coin and map the output 0 to 1, something like that. And we all know that it's 1, right? We kind of have have agreed to say that if the coin is a fair coin, what do we say that the probability of your observing 0? 1/2. That kind of idea is related to this event space and the probability measure. So precisely speaking, we have to say something like this. This P is actually a function again, okay? So see that? This is a set, okay? This is a collection of some or all, this is subtle, subsets of this. And this P accepts the elements of this event space. And this P assigns a real number from 0 to 1. Okay? So P is again a function. And you can say like this. And some of you have been taught this major theoretic concept, but some are not familiar with it. So let's think about more concrete example. So suppose this source, random source itself, generates the number from 1 to 6. Like we roll a die, okay? We roll a fair die. Then in that case, what is the sample space? Sample space consists of these 6 numbers. And what is the event space? Event space consists of 2 to the 6 subsets of this sample space. What is that? First, the empty space. And Second, the 6 individual atoms. And we have 2 out of these 6, blah, blah, blah. And eventually we have the sample space itself. Okay. So as you've learned in high school math, since we have 6 possible outcomes of this box, how many subsets do we have? 2 to the 6 subsets. 1, 7, blah, blah, and you have 2 to the 6. And what's the role of the probability measure P? If you have a fair die, then the fair die must map, right, the empty set to 0 and each individual atom to 1/6. And what about this? Something like this. And you have to, oh, sorry, it's or, so 1/3, right? And eventually you have this. And you may say that, wait a minute, do we really need all the mappings for each event? And your answer is no, right? You don't need that. Why? Because this P is not an arbitrary mapping rule. We are talking about that function as a probability measure. Okay? What does that mean? Probability measure, according to the Kolmogorov again, must satisfy 3, sometimes 4 conditions. And probably you've seen them as axioms of probability when you're an undergraduate student. What are they? Anybody? The axiom, sometimes, depending on the textbook, the first line is that the probability of empty event is 0 and probability of sample space is 1. Well, some textbooks say that probability of an event equals 1 minus probability of the complement event, something like that. And they start in that way. And what was the second thing? Anybody who remembers? Right. As we've seen here, the output of this probability measure must be less than or equal to 1 and greater than or equal to 0. And what? The last one is the most important axiom for probability measure. What is that? That has even a name. Countable additivity. What is countable additivity? Countable additivity means that if you have a sub i's, they are all the member of event space, which means that these AIs are events, okay? Events in the event space. For example, A1 could be 1, A2 could be 1, 3, A3 could be 6, A4 could be empty set, something like that, right? So given that, if AI intersection AJ equals empty set for all I not equal to J, then this probability measure must have some interesting property. What is that? Union of all I. Okay. Of course, here I is a discrete index. So here discrete set means that it consists of countable number of elements. It could be countably infinite, like the set of all integers. Anyway, and you must have. Okay. This is the third axiom or third requirement named countable additivity. Why it is named countable additivity? Because we have a countable set or a discrete set for the index. Okay, sorry, not equals. It's a member of. Sorry. And why we have additivity? The probability of each individual events are added to result in the probability of union of these disjoint events. By the way, if you have a countable number of events and they all satisfy this one, we say that they are mutually exclusive or they are mutually disjoint, or sometimes you drop mutually, they are disjoint sets. Got it? Anyway, so this is the kind of major theoretic definition with a lot of hand waving. Okay, you may assume that this event space is simply the set of all possible subsets of S. However, that only is true when you are handling a countable sample space. If you have uncountable sample space, then you have to remove some of the subsets of S when you form the event space. And the reason why you require that, in order to explain that, you have to take major theory course. I cannot explain. This is difficult, okay? But you don't need that. As an electrical engineer, I'm very sorry, you are not going to become a PhD in mathematics. So I have to say that there is a notion of sigma algebra. And that is related to, that is a core concept of major theory. And you need to take a course called major theory, or in Korean, 축도론, to understand that. But according to my experience, we don't need that level of rigor. What we need is this. When we talk about major theoretic definition of probability, we have a sample space that is very easy to understand because it consists of every outcome of this source, some random experiment. But this event space sometimes cannot consist of every possible subset of the sample space because of that sigma algebra notion. Because people have found that whatever rule we make, that is broken by some strange sets. We cannot assign consistently probability to some of strange events. So what we do is that we do not just talk about such event. One good thing is that mathematicians and electrical engineers have found that those sets we don't need to think about because they are pathological sets, and we don't need to take them into account. So you just need to understand this way. Okay. Given a sample space, we have to have some event space to evaluate this probability measure. However, not every subset of sample space is to be evaluated by the probability measure. But it's okay. Right? That's our compromise. Now, using this major theoretic notion, let's, for example, review the definition of a random vector. Now, what was your undergraduate level definition of a random vector? It was a collection of a finite number of random variables with well-defined joint CDF, cumulative distribution function, or a PDF, or if you want, probability mass function, right? So your undergraduate version of a random vector X was something like this. We have finite, right? N, and we have joint CDF or joint PDF or joint probability mass function. Got it? Now, what my question is, what is the counterpart to this one? But now a major theoretic definition. And we follow the same approach. It's like, again, here you have some underlying probability space, and you have a random something generated. We don't know, okay? But it generates an element S following this underlying probability space. Now, in order to have a vector here, what do you need? This S must be mapped to, for example, n real numbers. So it's a vector valued function of S. That is a random vector. So you have x1 of S up to x of n of S. And each one is a measurable function. Here, measurable means that inverse image exists, blah, blah, blah. But anyway, you need just put measurable whenever you have a function. Got it? Then it sounds like you are knowledgeable about measure theory. Anyway, so do you see the commonality? So when you're an undergraduate student, you had this idea. Okay, here is a random source, and we have a vector with some uncertainty. And that uncertainty is probabilistically described by the joint CDF, joint PDF, or the probability mass function. That was your undergraduate version, non-major theoretic definition. Now you have a graduate version of a random vector. Here you have a random source with abstract probability space, and its outcome is mapped by a vector valued measurable function or measurable functions. And here you have some real vector valued signal. Now, let's extend this one to anything. Now let's consider the non-major theoretic definition of a random process. Especially, for example, let's consider a discrete time random process. What was that? According to my last time definition, a discrete time random process is precisely speaking is what? Discrete parameter random process. And in most of the cases, the parameter is related to the time unit. So we just say discrete time. But anyway, discrete parameter. What does that mean? Our subscript index is a member of a discrete set or a countable set. So what do we have? We have infinite, but countably infinite number of random variables. So do you see the difference? We started from a single random variable. We moved to a finite number of jointly distributed random variables. That is a random vector. Now we have a countably infinite number of random variables. That is a discrete parameter random process. And last time I said that according to Kolmogorov, how can we probabilistically fully describe a discrete parameter random process? We provide you all possible finite order joint PDF or CDF of those random variables, right? You take some of them. However, always some finite number of them. And these CDFs must be consistent. They should not contradict each other. For example, you have joint CDF of first and second random variable. You marginalize, and you get two marginal CDFs. And these marginal CDFs derived from the joint CDF must be the same as the individual CDF, right? That is consistency. And that was the notion of a discrete time, a random process. Now, what is our graduate version of? What is our graduate version definition, major theoretic definition of a random process? And we just remember what we've done for a random variable and a random vector, variable and random vector, okay? We do the same thing. We consider a random something generator governed by or described by an underlying probability space consisting of the sample space, the event space, and the probability measure. And we have some sample S, outcome S, and here goes what? What should be the output? Output should be some, according to our undergraduate version, something like this, right? Then what should we have here? And here comes the difficulty in notation. So I'm going to just write it this way, okay? As we've seen, as we've done in describing a random vector. So X subscript N, okay? And then what do we have? Given S. This mapping rule must map an element of sample space to what? A real valued sequence, right? So it must be dependent on S, and it must be dependent on N. You may put it here, or you may put here, or what? What you can do is this. You can also do something like this. So how many measurable functions do you have? And here, this could be replaced as this one, right? So when you have a random variable, you have a single measurable function that maps S to a real number. If you have a random vector, you have finite number of measurable functions that maps S into real numbers. And if you have a discrete time random process, then you have what? Countably infinite number of measurable functions that individually maps S into real numbers. And we have this index, discrete index. Got it? Okay. Or sometimes you can just simply say this one. Now, let's consider a continuous parameter random process. So in your undergraduate version, you had something like this, right? You said that, okay, it's a time function with uncertainty. So when I have no uncertainty, I usually call the lowercase x of t. So let me just use capitalized x of t to denote a continuous time random process. Now, what is your graduate version? Here comes the difficulty. How many measurable functions do we have? Now we have uncountably infinite. So if I draw this way, it somehow implies countability, right? So usually we don't do that. What we just usually do is some textbook has this notation, or some textbook has that notation. Anything you can use. What is important is this one. Anyway, given S, given the outcome of the random experiment governed by that underlying probability space, what you do? Given each S, right? So you fix S. Then what do you have? You have a time function, right? So it's like here resides a grad and gives you some value of S. And here you have an angel that just follows the order. Okay, what kind of S? Okay, got it. S is 0. Okay, let me check. Okay, here is the continuous time function that must be generated when I have S0. Now, if you fix S here or there, it depends on the preference of author. But anyway, if you fix like this or that, okay, then what do you have? What is this one now? It's a function of t, right? Here S0 is fixed, okay? So fix S0. Then what are these? They are, this is a deterministic function of t, especially deterministic continuous time signal. Same happens for the discrete time case. Suppose you fix here, then what happens? You have x sub n of some S0 for all n, right? Then what? You can say this, okay, I have something like this. Okay, notation is messy, okay? However, you may say that given S0, I have a deterministic discrete time signal. These discrete time, deterministic, discrete time, or continuous time signals, individuals are called sample paths or sample functions. Okay, so here comes the notion of sample path. Sample path is merely something when your mapping rule to generate the random process has this S, value of S fixed. So usually, let me ask you a question. So how many sample paths do you have? How many? In general. How many? Infinite. Okay? In general, depending on the size of the sample space. Okay? Sometimes you have only 2 sample paths, or sometimes single sample path. In that case, what can you say? If the probability of observing that sample path is 1, you may say that, okay, I will forget about random something. It's a deterministic function. Got it? So now you have these two. Your signal gen systems with all deterministic discrete time and continuous time signals is a special case of random process related course. So I remember this around 10 years ago when I was teaching undergraduate probability and random processes course. I put a final exam problem like this. I just gave them a deterministic signal and compute the power spectral density. And many of the students says that you never mentioned the power spectral density of a deterministic signal. In this course, only we learned how to compute the power spectral density of a random process. 0, right? Because a deterministic signal is a special random process. So you can just use the definition of the power spectral density of a random process to compute the power spectral density of a deterministic signal. Got it? So now you may say that, okay, this random process is a generalization of a deterministic signal. And similar thing, actually the probability theory itself is a generalization of logic. Okay? So as an when you're an undergraduate student, you as an electrical engineer, you have been taught or have taken the digital circuit course, elementary digital circuit course. What did you learn? Boolean algebra, right? And or not. Those things are all related to the logic, right? Probability theory is a mere generalization of that logic. The difference is that in that theory, you have certainty. Okay, this is true or false at that time. But now, what do you have? This could be true with probability 0.3. Okay, that's the difference. So probability theory is an extension or of logic. You have to remember that. Okay, anyway, so as I promised in the beginning of today's meeting, I said that we are going to link the non-major theoretic definition of a random process and major theoretic definition of a random something. Now you have some idea, right? You have to divide a single source when you learn that is learned in undergraduate into two things. That is the trick, okay? And this entire serial interconnection corresponds to this block. And here you always have some underlying probability space and a source that is governed by this triplet. Then whatever you have, random something, here you have a mapping rule that maps S into something. If this was a scalar with uncertainty, this is a single measurable function. If this was a vector with uncertainty, this consists of finite number of measurable functions. If this is a sequence that starts from 1, we are going to study after this chapter 9. We are going back to chapter 7 of the textbook, where a sequence of random variables are covered. Anyway, if you have a sequence with uncertainty, then you have what? You have a countably infinite number of measurable functions that are indexed by or subscripted by 1, 2, 3, 4, something like that. If you have a discrete time signal where time index n could be any integer, then again you have countably infinite number of measurable functions now indexed by an integer. Okay? Negative 1 million, negative some anything, positive anything, 0, something like that. If this is a continuous time with uncertainty, what you are going to do? You have now an uncountably infinite number of measurable functions that is now hard to visualize because we cannot count. In that case, you may say that, okay, here is a measurable function that accepts some S, and if that is fixed, then we have a continuous time function. Got it? Now, let's extend that idea. Now extend this idea. How can we define a random graph? So what is a graph? A graph, undirected graph, let's say. Graph consists of sometimes nodes or edges, right? Or edges, vertices, but anyway. So a graph consists of so-called dots and lines, right? Now, you want to define a random graph. How? Again, you have to define something here so that you have a graph when the input is some outcome S. Okay. What is a random polynomial of order 3? You can define something here, okay? Something measurable thing, okay? To have the output of that one, a polynomial. So in this way, you can define measure theoretic anything, measure theoretic random anything using the same template again and again and again. Got it? Okay. So that is the kind of the most important lesson of today's meeting. Then, what's the role of Kolmogorov's existence or extension theorem? What is the role? Kolmogorov's extension theorem says this one. Suppose you have non-measure theoretic description of a random process. What does that mean? You have every nth order CDF well-defined, and they are consistent, right? And Kolmogorov's theorem says that if, for example, you have a discrete time random process described in terms of those nth order CDFs, then Kolmogorov's extension theorem says that there exists, he didn't find, he proved that there exists an underlying probability space and what? And countably infinite number of measurable functions. They generate the same. So it's like Kolmogorov's extension theorem says that even though we just do not use any measure theoretic thing, we just use CDFs. But he says that, okay, if they are consistent, well-defined, then you can just assume that there exists a random source that is governed by some abstract probability space, and there exists a sequence or countably infinite number of measurable functions. Got it? So these things exist. That's why the theorem is called existence theorem. Okay. Or conversely, suppose you have a continuous time random process, measure theoretically defined. Okay. Suppose you have defined some abstract probability space, you have defined uncountably infinite number of measurable functions. Then Kolmogorov's extension theorem says that you can find, or you must be able to find all nth order CDFs. And they must be consistent. Got it? So Kolmogorov's extension theorem enables us to use both of the undergraduate version and measure theoretic version of definitions of some random something, especially random processes. Got it? And if you think about the random vector or random variable case, it sounds very obvious. But when we talk about a random process that involves infinite number of random variables, it's not easy actually. So that's why I say that, okay, we are not going to be that rigorous. However, we want to have some knowledge, some working knowledge about measure theory related definition. Got it? Okay, let's quickly read the undergraduate material very fast. Okay, first, as an electrical engineer, we usually use those mathematical entities like scalar, vector matrix sequence, discrete time, signal, continuous time signal, field, polynomial, graph, those kind of mathematical entities to describe what? Signals or systems, right? Yeah, we use that. We use those mathematical entities to mathematically describe our signals and systems, electrical signals and electrical systems. The problem is that we have to consider some uncertainty in these electrical signals and in these electrical systems. Then what do? That was our undergraduate motivation. So we introduced counterparts. For the scalar, we introduced the notion of random variable. So scalar with uncertainty, vector with uncertainty, matrix with uncertainty, sequence with uncertainty, discrete time signal with uncertainty. What is that? A discrete time random process. Continuous time signal with uncertainty, or continuous time random process. Be careful. There is another way to handle uncertainty based on so-called chaos theory, chaotic approach. They use deterministic idea, and they say that every uncertainty is actually not related to some pure random sum. It's deterministic, but we have some problem in observing everything. They have different view. We are not talking about that. Of course, there are some, especially control engineers, who really love this idea of chaos theory to handle uncertainty. So be careful, okay? This probabilistic approach is not the only one approach to handle the uncertainty. Got it? So as I told you, in 10 years, if I meet you, okay, oh, it seems you have taken my course 10 years ago. Okay, what is the other way to handle uncertainty in signal systems? And you may say, what you are talking about? You have to say this. Yeah. One approach is based on probability theory. The other is based on deterministic but chaotic approach. Got it? But I'm not talking about. Okay, so we are talking about random time functions with uncertainty. And examples are, especially in digital communications, bit stream. We usually assume that, okay, bit 0 is occurs with probability 1/2, bit 1 occurs with probability 1/2, blah, blah, blah. And also we have to talk about noise, thermal noise in radio frequency components like antennas, amplifiers, mixers. By the way, sometimes random process is called stochastic process. Stochastic has Greek root, and the meaning is exactly the same, random. Okay. However, they are not fully interchangeable because of probably rhyme, I don't know. But usually what we say, random variable, not stochastic variable. Got it? We say random vector, not stochastic vector. However, for random process, many people prefer saying stochastic process, even though I prefer random process. Got it? So you have to have that idea. Okay. We have to be more quick. And this undergraduate material just talks about measure theoretic definition of a random process. That confuses our undergraduate students a lot. But anyway, so given a probability space consisting of a sample space, event space, and a probability measure, usually when you say that, okay, you are given a probability space, then this is given, that is given, and this is also given. For example, you have 2 coins. One is unbiased and the other is biased. In that case, the difference is that the 2 random experiments have the same sample space, heads and tails in the set, same event space for possible events, right? But the probability measure is different. For the fair coin, the probability of heads and probability of tails must be the same and 1/2. For the biased coin, this probability measure is different. For example, probability of heads is 1/4 and probability of tails is 3/4. Got it? And a random variable, this is a reminder, is a function, measurable function from the sample space to a real line. Okay. So be careful. This probability measure maps to the interval 0 to 1. But this S, if it is a real valued random variable, its output is a real number. Then I can immediately ask you this question. what would be a random, complex valued random variable? Same thing, right? Any random something can be measured theoretically thought in this way. You have a random outcome generated governed by a probability space. Now you have a measurable function that accepts this outcome S. And you must have some complex number. So this measurable function is now a complex valued measurable function. Or you may say that, okay, mathematically it consists of two real valued measurable functions. One output will be mapped to the real part of that complex number. The other one will be mapped to the imaginary part. Got it? So mathematically speaking, a complex valued random variable is equivalent to a two-dimensional real valued vector random vector. Got it? They are the same mathematically. No big deal. However, it's very subtle in electrical engineering to handle a two-dimensional real valued vector and a one-dimensional complex valued scalar. Sometimes it's much easier and much straightforward to understand or handle a complex valued signal, scalar, rather than two-dimensional real valued thing. Because you need some just multiplication, conjugation, addition. But here you need possibly vector matrix multiplication or something. Sometimes this helps you. Sometimes directly handling them as complex valued helps you. So you must be able to have two tools at your toolbox. Got it? As we have now in non-measure theoretic undergraduate version of understanding of random something. And also now we have all measure theoretic definition of random something, right? So you now have two tools to define random something. You now have two tools to handle two-dimensional random vector or one-dimensional complex random variable. Got it? So you know what this means, right? You have an abstract random experiment that generates some outcome, given that you have a sample path. Okay? That is a random process. So random process is a two-parameter function. If you have a real valued random process, this function is a real valued measurable function with two parameters. One is what? Decided by that outcome. The other is your time index. Okay. By the way, here goes a very, very simple example. Instead of using this x of t comma s or x of s comma t, that this notation that is precise, but we use this easier version of notation. And this notation is what we usually use and what we have been using since we have taken undergraduate course. But this is a kind of shorthand notation of that one. Because we don't, in case we don't want to talk about underlying probability space and some strange outcome. Okay? Sometimes we have no interest in that, right? We just know from Kolmogorov's extension theorem that, okay, there exists, or we may assume there exists some underlying probability space that governs this random experiment and outcome comes, and this S is mapped to a sample function. We know that, but we don't want to talk about that in many cases. In that case, just use this notation. But you have to know, actually, this notation is shorthand notation of that one. Got it? So let's see. Suppose that this abstract random experiment generates heads or tails with different probability. And now this mapping rule either generate cosine 2 pi t or sine 2 pi t, depending on what was the input to that measurable function of two parameters. If it was has, then it generates this time function, or it maps to this time function. If it was tails, then the box maps tails to sine 2 pi t. Now, in this case, how many distinct sample paths do you have? 2. You only observe that one or that. Got it? Okay, what else do we have? Oh, by the way, the collection of sample paths or sample functions is called an ensemble. Okay, so here the family of time functions, sample functions, is called an ensemble. Got it? What else? Okay, sample function is sometimes called an ensemble member, or sometimes a realization of the process. They are all interchangeable. As I told you, sometimes you use this notation. Here, you see, all the subscript is to count or distinguish different random variables, right? This t could be an integer, this t could be a real number. If this t can only be an integers, then we talk about a discrete parameter or discrete time random process. If this t can be any real number, we are talking about a continuous time random process. Got it? So there are many, many different notations. Here, again, we repeat again and again. If t is a variable, x is fixed here, then what? We have a deterministic function that is called a sample path. Got it? If s, this is an important idea, and this links the undergraduate version of the random process to the graduate version. What if s is a variable and t is fixed? So here, this t is fixed to, for example, 0. Then you have a single measurable function of s. What is that? A random variable. Okay. So suppose you observe cos p 200 from today at time 12 o'clock. Then you have a random variable. Okay. So random process evaluated at a specific time is a random variable. And let's see some figures because I'm talking too much. So suppose you observe some random process. Okay. It could be this, it could be that, or that, or that, and dot, dot, dot. Okay. So these are, for example, sample paths of a continuous time random process x of t. And probably they are different because the outcome from the abstract random experiment generator is different. Okay. Now you fix, for example, t equals t1. Then what do you have? You have scalar with uncertainty. What is that? A random variable. Suppose you have two time indices, t1 and t2. Then you have two random variables, and they are jointly distributed because of the Kolmogorov theory. Now, here goes some sample paths or sample functions of a discrete time random process. Suppose it is obtained by uniformly sampling a continuous time random process. Okay. And here, again, if you fix n equals 0, then you have what? A random variable. If you consider two time instances, then you have a two-dimensional random vector. You can obtain a two-dimensional random vector. If you sample at three time instances, then you have a three-dimensional random vector. Got it? And this type of signal could also be a random process. And that one too. Got it? Have I covered all the things? Yeah, I believe so. By the way, some people use this term, digital process. And this is related to the difference between a discrete time signal and a digital signal. The problem is that when the circuit guys talk about digital signal, they have the concept like this, okay? It's a continuous time signal, but its value is discretized or approximately discretized. So this is a continuous time axis, and at every tick of the clock, then it moves to 5 volt or 0 volt, something like that. Sometimes you have actually transition. So its value could be from 0 to anything. Sometimes it overshoots, undershoots, but they say it's a digital signal. However, in my area, signal processing, communications, control, when people say a discrete time signal, they have a sequence of numbers, mathematically speaking. So it's a really discrete in time. And moreover, when they say it's digital, we have one more thing. It's a discrete time signal with discrete possible value. Got it? So digital means different for the circuit guys and for the systems guys. Be careful. Sometimes we need to classify these random processes. Otherwise, we can't say anything. In signal gen systems, because you've taken, most of you have taken signal gen systems when you're an undergraduate student. In the beginning of the course, we kind of classify the signal gen systems. You remember? Yeah. Periodic signal, non-periodic signal, finite energy signal versus infinite energy signal, like sinusoidal signal, or finite power signal, or zero power signal, or what? And for the systems, linear system, nonlinear system, system with memory, system with no memory or memory system, linear system, nonlinear, time invariant, time variant, something like that. Why? Of course, sometimes a classification is mere a classification. However, in sometimes this classification gives us a much more bigger result. Like, for example, okay, let's consider a subset of linear systems. Let's consider subset of time invariant systems. Then at the intersection, linear time invariant system, so we kind of narrow down our interest, then we have an amazing result. What? The system can be described by a single function called the impulse response. And moreover, you have a tool, so-called Fourier analysis. What does that mean? If you have a linear time invariant system, then the impulse response is Fourier transform. That is called frequency response. That relates the output Fourier transform and input Fourier transform through what? Mere multiplication. So output Fourier transform is simply multiplication of input Fourier transform and impulse response is Fourier transform. Amazing, right? So in this way, some classification really useful. You have a theory and you have now what? A single mandatory undergraduate course, signal gen systems. Of course, there are other things, right? So you have to learn as a graduate student, linear time varying systems too, right? Sometimes you have to learn nonlinear systems to handle nonlinear electrical systems, right? Design nonlinear electrical systems. They are actually very messy. However, this theory of linear time invariant system is very, very useful. Similarly, for the random processes, same thing. We classify random processes. And sometimes, even though it looks initially an arbitrary, just mere mathematical classification. However, you can develop a theory. And that is also important. Okay? So the lecture note talks about how to classify random process. First one is not that important. Okay, so this classification, deterministic versus non-deterministic. So you have a set of random processes. You have deterministic, non-deterministic. This is not that important. However, the reason why the textbook usually talks about this notion is because it's confusing. Remember that I said that you have a deterministic signal, then it's a special random process. That's what I told you. Here, deterministic and random process does not mean deterministic signal, does not necessarily mean. It may be indicating a deterministic signal. However, it's kind of a bigger concept. And it says that deterministic means that if you observe a realization of a random process up to some time instant, then you can perfectly predict the future. In that case, it is a deterministic random process. And can you give me an example? We've already seen. Where it is? This one. See that? This random process is not a deterministic signal, right? Because with probability 1/3 you observe cosine, and probably 2/3 you observe sine. So there is uncertainty, definitely. However, suppose you have observed a realization of a random process up to, for example, -infinity to 0. Then actually, if you observe at time 0 and it's 0, then that sample path can be perfectly predictable, right? Because it's a cosine function. Because at t, this cosine is 1 and this sine is 0, right? So this random process, even though it has uncertainty, it's a deterministic random process. Got it? Not that important, but sometimes it's confusing. That's why the textbook and I talk about this classification. By the way, almost every meaningful interest of our interest, the random processes of our interest are non-deterministic random processes. That's why we need a theory, okay? Most of random processes of interest are non-deterministic. However, sometimes we really have deterministic random process. Let me talk about one more minute because it's important. When we have Professor Hong-Jun Park, the circuit theory professor who recently retired with my department, one day he approached me. Hey, Professor Joe, I have a question. I believe you may answer this one. And his problem was this one. At that time, the so-called handheld device manufacturers really wanted to develop multi-touch screen. These days, multi-touch screen is just popular, right? But at that time, you could only do the single touch. And his problem was this one. Due to the clock included in the handheld device, there was a periodic noise. The period was perfectly known. However, due to sometimes depending on the time of your turning on, the exact time instant of that noise, peaking noise, was unknown. And he approached me, hey, Professor Joe, how can I simply suppress this noise? And his students had some idea, but solution was not that working well. So I said that, okay, there is uncertainty in offset, but the period is given because of the clock. So I said that, okay, it's a what? Deterministic random process. Okay, ignoring the amplitude, okay? Then we can do very simple thing to suppress that. So what I proposed was this, because in his case, he could generate some signal. So I said that, okay, Professor Park, generate a signal, control signal that changes polarity with the same period. Then what you do is that you multiply 1 and -1, then what happens? My signal adds up to positive values. That noise, some value V and V now becomes V minus V, right? So it's like 0 V volt, 0 V volt, right? And my signal A, -A. And I cut just 2 periods. And for this one, I multiply 1. For this one, I multiply -1. My signal adds up, noise cancels each other, right? So very simple. So when you have a deterministic random process, it's very, very simple. However, unfortunately, we mostly do not talk about deterministic processes, believing that it's too simple. Got it? However, remember that there is a very simple, easy to handle class of random processes, deterministic random process. Got it? And remember my example. Okay, that's all for the day, and let's continue next week.